Journey here. So last time we got into chapter 12 officially, and in chapter 12 we were looking at alcohols, and we talked about obviously the functional group of alcohols is the OH group. Remember that is a polar group with the oxygen being more electronegative, the hydrogen being more positive. And as we talked about, that attributes a lot of some properties that we see with alcohols, including the ability to hydrogen bond with things like water and themselves. And that makes things that are alcohols soluble in water. And again, that is, in terms of being soluble in water, it is dependent on how many carbons there are. So again, once you start hitting that 5-ish or more sort of carbons, solubility really starts to come way down because you have a much larger, as we talked about, sort of non-polar part of that molecule versus the polar part. But relatively small alcohols, because of its ability to hydrogen bond with that OH group, will definitely be soluble in water, things like methanol, ethanol, and so forth. Also, it gives alcohols a high boiling point and melting point, and that also is because of the ability for alcohols to hydrogen bond with themselves, which is a relatively strong attractive force, and thus means that it'll take a lot more energy to break them apart to get them into the gas phase, which is what happens at the boiling point. And the result of that is you'll see a higher boiling point typically in alcohols versus a lot of other organic groups. Pretty much most organic groups are going to fail in comparison to alcohols in terms of boiling points or melting points. There's a couple of things that could kind of get higher than an alcohol, but most of the time that's going to be your guy out there is going to be the highest boiling point and melting point because of its ability to hydrogen bond. Definitely much higher than alkenes, alkanes, alkynes, which although they do have hydrogens, again, they do not have the ability to hydrogen bond. Reminder that in order to hydrogen bond, you need a bond between hydrogen and either nitrogen, oxygen, or fluorine. So typically for something to hydrogen bond, it needs to have that hydrogen that is directly attached to one of those three elements. And that is because those elements are the most electronegative ones that you could have. So it creates a really polar bond. And that's why the OH group is obviously the hydrogen directly attached to the oxygen, creates that pretty good polar bond. We talked obviously about naming alcohols, and they do end in OL. We also do give the priority to the OH group. So that priority in terms of numbering the carbon chain, you want to go whichever way is going to give that OH group the smallest number. And right around 3 or more carbons, there becomes an option as to where that OH group could be located. So right around 3 or more carbons, you also need to give the location of where that OH group is located, like 2-propanol or 1-propanol, much like what we do with a double bond or triple bond, where there's multiple locations as to where those guys could be attached. You do have to give the location of those. Remember that because of the OH group gets the priority in terms of numbering, that once you lock yourself into place in terms of whichever way you're going to number to give that OH group the smallest number, then any other group that may be there needs to be named or numbered accordingly based on how you numbered for the OH group. We still put all of our other guys there in alphabetical order, regardless of the prefix and numbering for our groups. Now, we talked about some reactions. We talked about really the formation of an alcohol, and we get an alcohol essentially by doing an addition reaction of an alkene, where we add water, which is sometimes referred to as a hydration reaction. And when we do so, remember that in this type of addition reaction, we're going to make our double bond into a single bond. And that's going to allow room for each of the parts of water to basically attach. And water is basically added as hydrogen and OH. And in this case, it's a symmetrical addition, which really means that you can't go wrong because both carbons have the same number of hydrogens, which means you can put the OH on either side, and it's basically the same thing. And here is ethanol. So we go from an alkene to an alcohol through a hydration reaction. We also talked basically about the reverse of this reaction, which is a dehydration reaction. So again, if you had the alcohol, and you did some heat, which is referred to as by that triangle, we would basically be removing the alcohol. And much like it comes on, it gets removed the same way. We take the OH, and then from an adjacent carbon, we take a hydrogen. It doesn't really matter which one you grab. And that's going to give us our water that's going to come off. And once again, nothing else will change on our molecule here, except that, as we talked about, now that we sort of remove those two things, where you need to put basically a bond back in its place, and we'll get back our alkene here as we go this way from an alcohol, and that's a dehydration reaction. Any questions on either of those? Now, remember that technically speaking, as we did a couple examples, and we also talked about, remember that if you are doing really either one of these reactions, and there is a difference in terms of the number of hydrogens there are, where the double bond's located or where you're going to put the double bond, then it does make a difference as to basically where the hydrogen ends up. So the hydrogen should always end up, when you're adding in something like water, to the one that has the most hydrogens to begin with, if there is an option. And we didn't have it in this case, but for example, if there was another carbon on the right of that, and there's maybe an option where you could take off the hydrogen, when we take off the hydrogen, it comes off the one with the least. So to make the double bond and make the alkene coming back, if we should have that situation. Any questions on either of those reactions there? We then officially talked about, I think at the very end there, once again, the oxidation reactions that alcohols undergo. And a reminder that when we're doing oxidation here and reduction, basically, which, by the way, again, always occurs pretty much together. Usually in organic chemistry, we're looking at either the gaining again of oxygen as you go from reactants to products, or the loss of hydrogen as you go from reactants to products. Reduction is the loss of oxygen as you go from reactants to products, and the gaining of hydrogen as you go from reactants to products. So there are different types of alcohols, as we also talked about: primary, secondary, tertiary. So again, here, if we had our primary alcohol, and we were to oxidize it, which is again sometimes abbreviated with the little O in the box there, or the brackets. This definition again is the loss of hydrogen, or H2, and the way it loses hydrogen is it will always come off of the OH, and it will always come off one of those hydrogens from the carbon that's attached to the OH, and that's going to give us our H2. And once again, nothing else is going to change here on our molecule. It's going to be the exact same thing. But now that we did that, we do need to insert a double bond there between the carbon and the oxygen, which makes our carbonyl group. And as we talked about before, this is a primary alcohol, which gets oxidized to an aldehyde, which once again is another organic group, carbon oxygen double bond with the hydrogen. And as we also talked about last time, this aldehyde could also go through an oxidation reaction, kind of one more step. But this oxidation reaction is actually going to very simply add oxygen in there, and that will get us at that point Once again, not much changing here, other than we will insert the OH in there. And this gives us what is referred to as a carboxylic acid. And it has a functional group of COH, basically. So you can sort of take the oxidation of a primary alcohol to an aldehyde and then one more, from which you could actually obviously go back one step before the primary alcohol and do a hydration of an alkene to get to the alcohol, and then take the alcohol and oxidize it. We could have a secondary alcohol, and by the way, this is again a primary alcohol because the carbon that has the OH group is again directly attached to one other carbon. We could have a secondary alcohol that looks maybe something like this. And this would be, once again, a secondary alcohol because this carbon that has the OH group, again, is attached to 1 and 2 carbons. So that is a secondary alcohol. It is going to get oxidized. And once again, just like above there, that's going to include the 2 hydrogens. Once again, always in these alcohols, the hydrogen from the OH, the hydrogen here from the carbon. Once again, nothing much changing, except that we're going to take off those 2 things. And that obviously gives us our H2. And once again, just like above, we do need to basically pop in there a double bond between the carbon and the oxygen. And this gives us a ketone, where the functional group is 3 carbons in a row, where we have basically carbon-oxygen double bond there in the middle. This will not continue to oxidize at this point to anything further. Lastly, we can have a tertiary alcohol, which is, as we can see in this example here, attached to 1, 2, and 3 carbons. And when we go through an oxidation, we will get no reaction, as again, it is missing really the crucial sort of hydrogen to allow that oxidation to occur. So it has no hydrogen there. So it will not go through oxidation. As we talked about at the end, pretty much the reverse reaction for these two are the reduction reaction. So if you add hydrogen to your aldehyde, you will go backwards and make your alcohol, your primary alcohol. And if you add hydrogen there to your ketone, you will go backwards and make your alcohol. So it's basically the reverse of it. Any questions on that there? And we'll talk about that, I think, in a bit here. All right, so then let's continue on through our chapter here. So we talked about, again, some of these alcohols, methanol, which is also sometimes called methyl alcohol, sort of the common name. And that's sometimes how some of the common names are for our early alcohols here. Again, getting oxidized to our aldehyde, which ends in Al, and then our carboxylic acid, which is oic acid in this case. Ethanol, again, is that alcohol that you can get through the oxidation, and eventually will kind of continue to oxidize the CO2 in water. We also talked about phenols as well. Remember that phenols are benzene containing guys that have that OH group. Again, that is phenol, not to be confused, as we talked about last time, with this guy, which would be cyclohexanol, right? Again, no double bonds in that guy. So the 3 double bonds, or the circle, is the benzene ring, which gives it that phenol sort of look. All right. So any questions on alcohol so far? All right, let's talk about the next sort of organic group, which are thiols. Thiols are sulfur containing groups. And this is the functional group here. And if you ever have any experience with sulfur, sulfur doesn't smell so good. I'm assuming why we have a picture of a skunk here. I'm assuming. So sulfur is found in a lot of things that have some aromas like cheese, onions, garlic, and oysters. They actually put sulfur in gas so you could smell that it's actually leaking. Otherwise, there wouldn't be no smell and you wouldn't know it's leaking. So they do put that in there so you can kind of smell it. So to name thiols, let's not. So we're not going to name thiols. You won't be responsible to naming thiols. Just in case you're curious, you can see down there, one way to name it is basically just to put thiol at the end with the number of carbons there is. So that is methane thiol. That would be ethane because there's 2 carbons, and just put thiol at the end. You will not be responsible for naming thiols, but again, you do need to know obviously the functional group of it. So we're not going to worry about naming them really. But what you do need to know about thiols, as we'll talk about it a little bit here, but we'll take a look at it now, is actually the reaction that sort of occurs with thiols, though. When you have 2 thiols here, let's just say we have a thiol like this, and we have another thiol like this, maybe. So when 2 thiols basically come together, what's going to happen is going to lose hydrogen through like an oxidation. And when we lose hydrogen, what that means is we're basically going to take those 2 hydrogens out, and we will get H2. And then pretty much what happens is you just like squeeze everybody together. So you start here and you just keep going until you get here and just put everybody together. So we would have CH3, S, S, CH2, CH3. This is what is sometimes referred to as a disulfide bond or bridge. There's some amino acids that contain sulfur, which can do this. So that bond you do need to know. So if you oxidize basically or put together basically 2 thiols, you lose hydrogen and you basically just squeeze everybody together with the sulfur bonding to the sulfur to make that disulfide bond. As you can imagine, if I wanted to undo it, I basically would need to do the reduction, which is add some hydrogen to it. And it's going to break apart always right between the 2 sulfurs. And then really you could just draw the 2 parts. You could have this guy here, and then you could have this guy here. And then pretty much all you have to do is give each one a hydrogen to sort of complete the thiols to coming back in this case. So to put them together, we take out the hydrogen, which is basically like an oxidation. To reduce them back, we basically add the hydrogen back in and they break apart there. So you do need the functional group. You also obviously need to know this reaction here. Question on that one there. Why don't you try one here? Let me just do one here maybe. If I had this. Okay, so let's take a look. So if you can recognize again that you got 2 thiols, you pretty much know where you're just going to put them together. And sometimes it's easier if you want to just maybe redraw one of them so that the thiol groups are kind of facing each other. So if I take this guy, basically just kind of flip them around, we're going to get something like HSCH3. And the reason you might want to line it up like this is, frankly, you should know, hopefully you're just going to take out the H's. So you can basically just put a box around the H's. And now what you essentially have lined up for you is pretty much the product there. So you just need to copy exactly what's there. So we will take our CH3, we'll take our CH2. Again, I'm starting here, rolling this way. CH2. Obviously, the hydrogens there in the box we're not going to put, but we are going to put the sulfur before the box and the sulfur after the box. That's going to give us our disulfide bond as we go from here to here, and that's going to leave us this guy, and what comes out is our H2 out of there. Any questions on that one there? So again, for thiol functional group, you do need to know these two reactions, putting it together and basically breaking it apart. Any questions on that one there? All right. Now let's talk about another organic group, which are ethers. Ethers have the functional group of carbon, oxygen, carbon sort of run there. And that's our functional group. So it does contain, obviously, this oxygen between two carbons, and it will have a bent sort of structure like water. And that is because, again, if we kind of put the dots here on our oxygen, this is basically 4 electron pairs and 2 bonds, which will give us our bent, our V shape geometry like we talked about previously. So how do we go about naming ethers? Well, there's sort of the common way to name ethers, which is pretty much straightforward. You find the oxygen, and then pretty much you look to the group to the left, and that's a 1 carbon group, which is a methyl. You look to the group to the right, which is also a 1 carbon group, which is a methyl. So that is 2 methyls. You go dimethyl, and then you just put ether at the end of it. So for ethers, you do need to know how to name them, and we're going to go with the common name on this. The non-common name is you put OXY on the group, and the longer carbon gets just the regular name. So this would be something like methoxymethane, which would be the UPAC way of naming it, which we do not want to do. So that is methoxy, because that's a methyl group. You get the oxy, and then methane would be the longest carbon chain. They're both the same, so either one's the same in this case. But we will go with the common name here, which is dimethyl ether in this case. So here, if we look at this one, we can do our middle oxygen, and then the group to the right there is a propyl group. Group to the left there is a methyl group, and we do go alphabetical order here. So this would be methyl, propyl, and again, ether at the end of it. Just to show you how the other name works, the smaller group is the methyl group. So this would be something like methoxy, and then long name here would be propane, would be the IUPAC way of naming it. And again, we're going to go with the common name for these guys here. So naming ether is not too bad. We're going to go common name, pretty much find the oxygen and find the groups that are attached to it. Go left, go right, and alphabetize them, and you will have your name. So if we had this guy would be then, yeah, it would be, we have an ethyl group, right? And we have another ethyl group here, and that would be diethyl ether. as our ether group is located right there in the center, where we have our carbon, oxygen, carbon. Basically right there is our ether group. Yeah. All right. Ethers are used, to put people to sleep and surgeries and stuff. Uh, Over the years, they have sort of changed some of the ethers. They replaced a lot of the hydrogens with things like fluorine, which makes them less flammable. So these are all basically ethers. But again, you can see really our ether group right there: carbon, oxygen, carbon, carbon, oxygen, carbon, carbon, oxygen, carbon, and carbon, oxygen, carbon in this case. All right, so why don't you do each of these, write the structures for each of these guys: 3-pentanol, ethanol, diethyl ether. Let's do, since we just did diethyl ether, let's not do that one. Maybe let's do ethyl pentyl ether instead. Okay, so let's take a look. Just like we've been doing, we always want to kind of work our way backwards here when we're drawing it, and we want to look for clues. So the first big clue here is I see OL, which tells me this is an alcohol. And pentane tells us it's 5 carbons. So again, we're going to start with that 1, 2, 3, 4, and 5. Since it is a alcohol, we do need to put an OH group, and that OH group is going to be here at carbon number 3. And since we are drawing it, we could go either way in terms of 1. I'm going to go again with this guy's carbon 1, which means my 3 would be right about there. I'm going to put my OH group. And again, at this point, everything else is going to be hydrogen to get to 4 bonds. So we need 2 there, only 1 there, 2 there, and 3 there. This obviously would be our condensed formula that I just drew. Once again, you could do the line structure the same way. 1, 2, 3, 4, 5. My 3 would be right about there in that case, and it would look something like that. Any questions on that one there? All right, so ethanol, again, working backwards, OL is an alcohol, ethane is just really just 2 carbons. This case, you can't choose wrong, and we're just going to fill in our hydrogens, and we got something that looks like this. And any questions on that there? I guess if you want to do line structure, look something like that. Yes, well, any questions on that? Then we went with ethyl pentyl ether. So in this case, we know it's an ether, which means we should know that there is a carbon, oxygen, carbon sort of setup. So that's a really good place to start is with that. You know that this is the functional group for an ether, so might as well just start there. Now all we have to do, right, is go on either side of the oxygen and lay us up our functional groups, which is an ethyl, which is a 2 carbon group, and a pentyl, which is a 5 carbon group. The only thing you do have to watch out for is at this point, I already have a carbon on either side. So you got to take that into account. So if I wanted to put my ethyl on the left here, I would just add 1 carbon. That will give me 2. And if I wanted to do my pentyl, I would need 4 carbons to be added to the one I had there, which would give me my pentyl group. And now pretty much like everything else, it's just going to be our hydrogens. So we'll go with 3 there, 2 there. 2 there, 2, 2, 2, and 3. And once again, this would be our condensed formula in this case. If you were going to do line structure, you really could do the same thing. You could start with the oxygen, then just kind of draw a couple lines up, and those would be carbons, right, to the points there. Once again, we would need just one more down there to give me my 2 on that side. I got 1 up on top. That's 2, that's 3, that's 4, and then that would be 5 in that case. And then you would have it. So again, sometimes when you're drawing these ethers, it's good to maybe just start in the middle and just kind of work your way outward with that functional group. Just make sure, again, when you put that carbon in the middle, you take that into account when you're adding your remaining carbons on either side. Any questions on how to do that there? Okay. All right, so we've talked about a lot of the properties of alcohol, so let's just talk about a few more things about it. Obviously, our hand sanitizers are made out of alcohols. We classified alcohol, so we're not going to spend too much time on this as we've gone over a number of times at this point. But once again, you're looking at the carbon that has the OH group, and again, how many carbons are directly attached to that, giving us our primary, our secondary, and our tertiary alcohol in each of these cases. So if we were to look at this primary, secondary, tertiary, this would be this alcohol. First one would be secondary, right? As we got 2 carbons attached to it. By the way, the name of this guy would be, I would like that better. There it is. It's you to know. I knew if I give you a second, you'll get there. So we do need a number here, obviously, because it has more than 3 carbons. And in this case, obviously, going left to right, 1 and 2 would give that OH group the smaller number. So it would be 2-butanol. This guy right here would be primary, secondary, tertiary. It would be a primary, as again, it's attached to just 1 other carbon. The name of this guy would be, it would be propanol. Do I need anything with that? Maybe like a 1-propanol, as that's sort of the limit there, right? As to where you need the number, because if I put the OH group on this guy, it would then be 2-propanol. So here we would need a number on this, and obviously coming right to left would give that a number 1 in that case. Lastly, here we have our tertiary. Looks like 1, 2, and 3 in this case. And again, if we were to number this or name this, probably involving some numbering as well, I'm thinking that's probably our longest carbon chain. Remember, it does need to include the OH group, and that would be 2, 4, 5. So 5 should then be pentanol. OH group is located at carbon number. Yeah, in this case, doesn't matter which way you go. It really doesn't matter for both of them, actually, right? There is no difference. So you go left to right or right to left, you will end up with actually 3 for both groups that are there. So that is 3-pentanol, and to be joined here by our 3-methyl. I go up above there, 3-pentanol. In this case. Any questions on classification or naming of those guys there? Now, if it did make a difference, right? Let's just say, for example, we had this. What would this one be properly called? Probably. This is still 3-pentanol, right? As no matter which way you go, the OH is going to get a 3. But which way should you number it in this case? Left to right or right to left? So it doesn't matter in this case which way we go for the OH, right? Because they're both going to get me to 3. But so the next important thing would then be the group. And it does matter for that guy, right? And going left to right would give that one a 2 versus right to left, which would give it a 4. So you actually would want to number in this way. Again, although it doesn't make a difference for the OH group, it's kind of a tie. Then you want to go to the next important thing, which would be the groups that are attached. In that case, it does make a difference which way you go. And in that case, you would want to go to the right. And that would get you something maybe like a 2-methyl-3-pentanol in that case. Yeah. So some cases it doesn't matter for both things, like it does in that last example. And sometimes it does matter for, say, like the group versus the functional group. So remember, if it happens to be a tie, and this works the same way for double bonds or triple bonds, if it's like a tie, the next thing that's important are the groups that are attached. So you want to think about which way we'll give those guys sort of the smaller number if it does make a difference. Any questions on that there? All right. All right, so we talked about the solubility of alcohols, and again, it has to do with its hydrogen bonding ability. So when water comes in, it has no problem. The negative side and positive side of alcohol in the water able to interact through that hydrogen bonding, and again, makes it quite soluble. Those that have 1 to 3 carbons are very soluble in water. But as I mentioned before, as you do start to increase the sort of carbon part of those alcohols and it gets larger and larger, it makes it really harder and harder for water to kind of get in there and interact with just that one little OH group there. So you do see a pretty big drop in solubility as you approach about 5 or 6. Pretty much not much happening there in terms of solubility because the carbon part's too large, the non-polar part's too large. Remember that alcohols, for the most part, have really kind of 2 parts of their molecules. They have a non-polar part, which is pretty much where all those carbons and hydrogens are located. And then it has really a polar part where the OH group is located. And it's really that polar part, again, that is interacting well with water. And when it's really small, it's able to interact pretty good. And that's because, again, water is not a tremendously big molecule. So for things to be soluble in water, you have to first break apart water and water interactions, because before anything goes into water, you have a bunch of water molecules attached to each other, basically. So to remove those interactions, you have to kind of replace them with something similar and similar size as well. And as you start building out, sometimes it just gets a little bit too big. It doesn't really fit very well. I think maybe I used an example one time about parking a semi truck in the garage. You get maybe some of it in there, but it's not going to fit so right. And it's kind of the same idea here when you try to put, really large organic molecules, especially alcohols, that have these big non-polar parts. You're just not going to be able to interact really well, especially since they only have really that small polar part to it. And that's what we see on this table. You can see after about 3, you got some slightly soluble, which is pretty much insoluble. And then about 5, you're pretty much going to be insoluble in terms of its solubility. Again, just because that nonpolar part is very, very large. All right. Phenols, which are also alcohols, are slightly soluble in water. They have that OH group that can hydrogen bond with them. So there is some solubility with it. And it was once used as antiseptics. And again, it's going to do sort of like a acid-base sort of reaction where the water here is going to act as the base, and this guy's really going to act as the acid. It's going to send the H plus basically over there to the water, and that makes our H3O plus and our -1, and again, producing that H3O plus in solution. All right, indicate whether the following is soluble in water and explain. Would the first one be soluble in water? Probably not. It is an alcohol, but the problem here is 1, 2, 3, 4, 5, 6. This big non-polar part here is going to really pretty much make it insoluble in water. So insoluble. Here's ethanol, and that should be soluble in water. Again, it has the same OH group. less than 3 carbons, and that would make it pretty soluble in water as it's relatively small. All right, any questions on alcohols? All right, we're going to get to some other carbon oxygen containing groups, and these are aldehydes and ketones, for which we saw how we make them. Again, we can make an aldehyde really from a primary alcohol that gets oxidized, and we can make a ketone from a secondary alcohol that gets oxidized. So these are the end results of those oxidation. Once again, the aldehyde's functional group is a carbon-oxygen double bond and a hydrogen. The functional group there of our ketone is always a 3 carbon in a row situation, where the central carbon there has the double bonded oxygen to it. And this also means that a couple things about sort of where we find these functional groups in a molecule. Because the aldehydes have the H, that means that the H can never be interior, right? Because hydrogen could only have 2 electrons, which means the functional group for an aldehyde will always be found at the end, one end of the molecule or the other end of the molecule, and it's because it has that hydrogen that is present. That also means that really this carbon-oxygen bond here, which is the carbonyl group, this guy always will be kind of never at the end, because you kind of need 3 carbons in a row, which means the closest that the carbon-oxygen double bond could get to the end is like second to the end, yeah, because it needs that 3 carbons in a row. So aldehydes will find themselves at the end. Ketones will always sort of be within, never at the end in terms of the carbon-oxygen group. They both contain a very special group, which is known as the carbonyl group, and that is the carbon-oxygen double bond. And this is what is sometimes referred to as the carbonyl carbon, as it contains, obviously, the carbon-oxygen double bond. That bond, by the way, is a polar bond. And if you look at the periodic table, carbon, nitrogen, oxygen, they are all in the same row on the periodic table, and oxygen is further to the right, which means it's more electronegative, and that creates a polar bond between these two. So the oxygen is actually more negative here. The carbon is more positive in this bond, and that does help with some properties of these guys, the aldehydes and the ketones, in terms of their solubility and some other things. So when somebody says the carbonyl carbon or the carbonyl group, they're talking again about the carbon-oxygen double bond here, and both of these contain that. A carbonyl group in the aldehyde has at least 1 hydrogen attached to it, and as I mentioned, is always going to find itself at the end. The other one will be at least second one in the carbonyl carbon because of that. There is our sort of line structure way of doing an aldehyde. You just basically put our double bonded oxygen, and you do need to write the hydrogen. That is because if I left the hydrogen off of that guy on the right, what would that turn it into? It would actually turn it into a ketone in this case, which is how you would draw the ketone there. Again, with nothing written at the end there, then that's assumed to be a carbon, which would be a methyl group in this case, and that would be a ketone. So it's important, if you are drawing it in line structure, a aldehyde, that you do write the hydrogen in there at the end. Although we don't typically write hydrogens with line structure, you should include it here to indicate that it is the aldehyde group versus obviously the ketone group if you leave it off. So aldehydes may sometimes be written CHO, and if you see that CHO, it is basically this group there. So sometimes in formulas to write it like that. Sometimes in condensed formula still write it like that, although most people will sort of draw it out even in condensed formula, the bond. A ketone and the carbonyl group bonded to two alkyl groups or aromatic ring will have that CO sort of written. By the way, you can have obviously a ketone on a ring like that without the triple bond looking thing there. It should be just a double bond. So that would be a ketone, and once again, that is carbon, carbon, carbon basically happening there with our double bond. Now, if you had an aldehyde there, you would probably see it sort of drawn like this, off the ring like that. So you'll come and see it like that. For example, something like that. All right. So let's talk about naming aldehydes. So aldehydes are sometimes confused with alcohols because they're named kind of similarly looking. So alcohols end in OL. Aldehydes actually end in AL. Yeah, so AL is how we name our aldehydes. And there are some aldehydes that have common names. Like one carbon is known as formaldehyde. Perhaps you're familiar with that. Two carbons is acetaldehyde, propionaldehyde, and butyraldehyde are common names. We probably will not go with the common names here. We will go with the IUPAC way of naming, which is AL. I would say probably out of all the formaldehyde might be one that you should be familiar with. That is a one carbon aldehyde. So that is formaldehyde. But if I was to go with my IUPAC way of naming, which is AL at the end, it has one carbon, which means it's based off of methane. This is known as methanal, AL. So that would be methanal. This guy here is two carbons, which is based off of ethane. This would be ethanal, AL. Do I need to give the location of where the functional group is located? The answer is no, because it has to be at the end. So that has to be at the end because of the hydrogen. You do not need to give the location, but it is the functional group, which means if you were numbering, you should start numbering at the carbon of the functional group because it should take the priority. So let's just say I had something like, this, for example. Longest carbon chain that contains the functional group is 1, 2, 3, and 4, right? So 4 is based off of butane. This would be butanal, AL, right? Now I do need to give the chlorine's location, and because this is still the functional group, this guy's got to be carbon number 1 because it takes the priority, which means that's carbon 2, and my chlorine's actually at carbon number 3 in this case. So although we do not need to give the location of where the aldehyde group is located in the name for the aldehyde group, it is still taking priority in terms of numbering, and it is basically carbon number 1 for any other group that's attached. So this then would be 3 chloral butanal, AL, not OL. OL would make it a alcohol. Yeah. Any questions on naming that there? So here we can see we have our methanal, our ethanal, our propanal, and our butanal here as we go through it. Once again, you do not need to get the location of the OH group, but in each of these cases, technically speaking, that carbonyl carbon is carbon number 1 for numbering purposes if there are other things attached. All right, so why don't you give the name of this guy? Why don't you give the name of this one? Why don't you give the name of this one here? And why don't you draw, let's do for ethyl pentanal. Okay, let's take a look. We'll start here at the one that was on the page originally. It looks like longest carbon chain, obviously, that contains the functional group, which is right here. That's our carbon, oxygen, double bond with our hydrogen. That's 1, 2, 3, 4, 5 carbons, which means it is going to be pentanal. We do have a group right there, which is a methyl group. And once again, although we do not need to give location of the aldehyde group, this carbonyl carbon has to be carbon number 1 for numbering, which means our methyl group here will actually be a carbon number 2. And this would be 2-methyl, squeeze it together, pentanal in that case, yes. Any question on that name there? Coming to my next one. Looks like the longest carbon chain that contains a functional group. You can get it either way. You kind of go from here up and over, or you could just go straight across. I think 1, 2, 3, 4. Once again, that is our functional group there, which is our aldehyde. So 4 carbons is based off of butane, so that's going to be butanal. We actually have a methyl group here. And we have a bromol group here. Once again, because this is the functional group, that's got to be carbon number 1 there. So that's going to give me a 2, 3, and 4. So that's going to be a 4-bromol and a 3-methyl. Still need to go alphabetical here. So we're going to go with the, we'll go 4-bromol. Dash, I don't know if I'll squeeze it in. I'll go below 3-methyl butanal. Obviously all together, not squeezed down underneath. Any questions on either of those names there? That looks like to me a benzene ring, yes, that has a aldehyde group on it. So this would be benzaldehyde, yeah. So that would be benzaldehyde. Basically, just put shortened benzene. That's kind of like a group name, and they put aldehyde at the end of it. Any questions? By the way, if I did have a group attached to this, let's just say I threw a bromine group there, what would the number of the bromine be? It would be 2, which would be numbering the ring. And that would be carbon 1 where the aldehyde group is attached. And then obviously the bromine would then be at carbon number 2. Any questions on any of those names? Let us draw going backwards. So Al tells us it's an aldehyde and pentane tells us it's 5. So I'm going to start with 5 carbons. And since it's an aldehyde group, I need to do a double bonded oxygen and a hydrogen. And once again, since you're drawing, you know that group should be at the end, so you could put it at either end. I'm going to actually put it on the right-hand side here. So I'm going to put my group right there. Obviously, if you put it on the other end, it's all good. Now, because I did put my group over here on the right-hand side of my picture, that would mean that that is carbon number 1 for numbering purposes. Obviously, if you did it the other way, then that would be carbon 1 on the other side. And that's important for my ethyl group, which is at carbon number 4, which should be right about there, I think. That takes care of the ethyl. And now we're just going to fill in our hydrogens here. And now I think we got it there in that case, yeah. Once again, if you were going to draw line structure, kind of the same idea, you would start with the 5. So 1, 2, 3, 4, 5. And again, here we would want to put our aldehyde group at one end. So you could either do it like this if you like, but you should also draw the hydrogen. And then we would go, that would obviously be carbon 1, 2, 3, and 4. And then we would have something like that as an ethyl group. Yeah. Any questions on any of those there? Okay, let's pick up any questions on aldehydes, how to name, how to draw. Okay. So at this point, we're going to talk then about ketones in terms of how to name ketones. So when we name ketones, we sort of replace the E on the alkane name with ONE. So just like kind of ketone, ONE, that is sort of how you end up naming these guys. There are some common names where we do kind of do very much like the ether. You kind of take the carbon oxygen double bond, go left, go right, and see what groups are attached. So if we look at this one here, that's basically a methyl group and a methyl group, and that's dimethyl ketone. Here's a 1 and 2 carbon group and a 1 carbon group. So that's ethyl methyl ketone. So these are the common names. Again, we're not going to go with common names for ketones. We are going to name them using the IUPAC way of naming, which is, again, ending with ONE at the end of it. When we get to typically about 4 or more carbons, usually around 5, but I guess sometimes people use 4 as well. You do need to give the location of where the carbon oxygen double bond is located. So right around 5, as you can see here. So if we look at this one that we have on the bottom there, which looks like this, I think. Once again, when we look at this ketone, this is the functional group right here. We have our 3 carbons in a row and our carbon oxygen double bond happening right about there. So that tells us it's a ketone. We'll count up our carbons, and that is 1, 2, 3, 4, and 5. So that is based off of pentane, becomes pentanone. Now, in this case, we do need to give the location of where that carbon oxygen double bond is located. And in this case, it doesn't matter which way you go. You could go left to right, or you could go right to left. Once again, it's going to end up at number 3. So this is 3 pentanone, and that is where the carbon oxygen double bond is located. And right around 5 or so there are carbons. You need that. That's because if I had this. This guy would be how many carbons? 1, 2, 3, 4, 5. This would still be pentanone, but my double bond is now located at carbon number 2, right? So this would be 2 pentanone. So much like alcohols, much like double bonds, triple bonds, when it comes to a point where you could have that functional group, and in this case, the carbon oxygen double bond in at a different carbon, you do have to give the location. Once again, we do not need to do this for aldehydes because they will always be at the end. So because they have the hydrogen, but because the ketone has that 3 carbon run, once you get to 5 or more carbons, you do need to kind of give that location. Any questions on that there? We take a look at this guy down here. And I got a line going that way. So obviously this is cyclohexane. And once again, this is our 3 carbon run with our double bond, which makes it a ketone. So that is where the cyclohexanone comes from, as it is a ketone. It actually does have another group there, which is a methyl group. And once again, although we do not need to give the location of the carbon-oxygen double bond in the ring here, it is assumed that wherever it is carbon number 1. So that would be carbon 1, which means if I go clockwise, I'm going to hit my methyl there at a smaller number than if I went counterclockwise. And that is where the 3-methyl comes from. 3-methyl cyclohexanone. So if you have kind of like a cycloketone, you don't need to give the location of the carbon-oxygen double bond, but much like with the aldehyde, it will be carbon number 1 wherever it's located, and that will determine pretty much how you number other groups that may be attached to the ring. Any questions on that there? Okay, let's take a look. We'll start with the one that was originally there. First off, we see a carbon, carbon, carbon with the double bond there in the middle. So that tells us it's a ketone. So we're looking for the longest chain there that contains that. So it looks like it's 1, 2, 3, 4, 5. You get it 2 ways. You go straight across or you go straight and then down. We'll get it either way. So that's going to be based off of pentane. So that's going to be pentanone, as it is a ketone. Remember that we do want to give numbering this guy the priority to give it the smallest number. That's going to be 1, 2, 3, 4, and 5. We'll achieve that. We also need to include that number as it's 5 or more carbons involved here with our ketone. So that's 2-pentanone for the location of the carbon-oxygen double bond. Again, much like everything else, once you sort of lock into place the numbering, then obviously your groups are numbered the same way. That would then get us for methyl 2-pentanone. Any questions on that name there? Looking at the next one, I think just straight across here will give us our maximum number of carbons. That's 1, 2, 3, 4, 5, 6. Once again, if we kind of look in this area here, that is our ketone group right there. So that is 6 carbons. That's a ketone group. That's going to be hexanone, O-N-E. We do need to number the carbon-oxygen double bond to give it the smallest number. And in that case, we do actually need to go right to left, I believe, as it will make a difference. If we went the other way, our carbon-oxygen bond would end up at carbon number 4, which would be obviously larger. So again, we want to give the functional group the priority. So that means that this would then become 3-hexanone. And because that is 3-hexanone, that means there at carbon number 4 is where my chlorine's at. So that is a 4-chloral 3-hexanone. Any questions on that one there? Lastly here, got a little cycloalkane with our ketone group. Once again, that's a carbon, carbon, carbon. So that is your 3 carbons in a row with the double bonded oxygen in the middle, which means that is 4 carbons total. So that is cyclo butanone, O-N-E, based off of cyclobutane, obviously. Although we do not need to give the location of the carbon-oxygen double bond, it should be carbon number 1 for numbering purposes. To get to our bromine here, hang a left, which seems like the shortest distance to get there. So that would put our bromine at carbon number 2, and that would get us something like 2-bromol cyclobutanone. Any question on any of those names there? All right, so we're going to draw then. We're going to go backwards. I see ONE, which tells me it's a ketone, which means I do need a 3-carbon run with the carbon-oxygen double bond in the middle. Heptane tells me it's 7 carbons. Maybe I regret this. 1, 2, 3, 4, 5, 6, and 7. So 2-heptanone tells me that my carbon-oxygen double bond is at carbon number 2. And for me, I'm going to go here as carbon number 2. That's also quite important because if this is carbon number 2, that means right next door should be carbon number 3 for me. Obviously, if you went the other way, then yours would be at the other end. And that means that I should have a methyl group at that point. What is left again is just hydrogens. So we're going to go with 3 hydrogens there, 2 hydrogens, 2 hydrogens, 2 hydrogens, need 1 hydrogen, no hydrogens, and 3 hydrogens in this case. Any questions on that one there? Question on how to name ketones or draw ketones. Kind of similar to everything else. Just got to put the functional groups there in the right spot. All right, let's talk a little bit about some of these properties of aldehydes and ketones. So aldehydes and ketones, they can form hydrogen bonds with water, and it's through that carbonyl group. So once again, that carbon-oxygen double bond is polar, which means when water comes on by, it could hydrogen bond right about there between the hydrogen from the water and the oxygen from the aldehyde or ketone. The aldehyde or ketone cannot hydrogen bond with itself or anything like that, but it can participate in hydrogen bonding with something like water. So because it's able to participate in hydrogen bonding with something like water, you do have some soluble aldehydes and ketones. But much like everything else, that 5-ish or so carbons, you're going to start to see, again, a decrease in solubility. But upwards of that, you should be fairly soluble when we look at it. So here's a chart of that. So as you can see, upwards of about 4 or 5 carbons, we're going to be okay. But really about 5-ish or more, we're going to start to see the solubility really drop. And it's really the same reason. You're just going to build out more of the nonpolar part. It's going to get too big. It's not going to allow water to kind of get in there sufficiently to interact with the carbon-oxygen double bond. And you'll start to see a very big decrease in the solubility of these ketones. Some ketones maybe you're familiar with: acetone, propanone. Nail polish remover, the wonderful smell. Yes, when you open those bottles, people like to do in closed cars as they're trying to do those things, right? Formaldehyde, maybe you take in biology, also wonderfully smelling things, I suppose. Some important aldehydes along the way. These are some better, maybe smelling things and tasting things. Benzoaldehyde is what we see in almonds. Vanilla is also an aldehyde, as here's our benzoaldehyde sort of group. And our cinnamon there is actually a ketone, carbon, carbon, and carbon happening there, which makes it a ketone. All right, classify each of these as aldehydes and ketones, and why don't you also name each of these? Okay, so let's take a look. So obviously the first one here is a ketone. Yeah, we got a 1, 2, 3 carbons in a row, along with our double bonded there. So that would be a ketone. And this would be 1, 2, 3, 4 carbons. So that'd be something like butanone. Any questions on that one there? B is a aldehyde, right? So that is that group right there. And this is a 2-carbon group, which means this is going to be our ethanal, Al in this case. Once again, no number needed, as that group should always be at the end. Coming to C, also a aldehyde. There's that group right there. There's multiple ways you could get there, I think. You could get 4 going up and over, down and over, or just straight across. So 4 carbons there would make it butanal, Al. Although we do not need to number it, that should be carbon number 1, as that's the functional group, which means that's carbon 2, and carbon 3 is where we got a couple of methyl groups happening. So this should be a 3,3 dimethyl butanal. All right. And we do need to give the number twice, as that's 1 for each of the methyl groups that are there. The di, because again, we have 2 methyls in that compound. Any questions on that name there? Lastly here, carbon, carbon, carbon. So 3 carbons in a row with our double bond happening there. Going to give us a ketone. The cyclic ring there is our big guy, which is cyclohexane. And now because it's a ketone, going to become cyclohexanone. Once again, not a benzene ring, no double bonds happening in that guy. Yeah. Question on the identification. Obviously, that is a ketone, that last one, which is right about there. Identification or naming. All right, so name these guys here. Okay, so looking at A here, we could hopefully see our ketone group right about there. So that's going to be 1, 2, 3, 4, 5, 6 carbons. And because it's a ketone, that's going to be hexanone. In this case, we do need to give the location of that guy, which would be at carbon number 2. So that would be 2-hexanone in this case. Yeah. Any questions on that? All right, looking at the bottom one here, obviously we have our ketone. That is 1, 2, 3, 4 carbons, which would be butanone. This would be carbon 1, 2, 3. By the way, that's a chlorine, not a carbon, right? So that is going to be actually, that's bad numbering there. Let's go 1, 2, 3, and 4, maybe better. That would be 4-chloral butanone. Again, here, don't really need the numbering there because it's 4. So right around 5 is where you got to kind of put the numbering in. Any questions on these names here? I probably wouldn't mark it wrong, but technically speaking, you don't really need it because, again, in this case, it would affect, obviously, if we move the double bond to the guy to the left there, it would still be carbon 2 for it, but it would affect the name of the group if it happened to be drawn that way. But technically speaking, you don't really need it because there's kind of only one place you could put it, which is the kind of that second carbon, either left to right or right to left in this case, yeah. And it would end up being number 2, no matter which way you would put it. Other questions? Okay. All right, so we sort of talked about these alcohols reactions a lot of times, so I'm just going to kind of scroll through it and get to some of the new reactions that we talked about. Obviously, we talked about the dehydration reaction. We talked about our oxidation reactions of our alcohols here earlier on, and our secondary alcohols as well, and taking our aldehydes to our carboxylic acids. And our tertiary guy there. So we talked also about, again, you are responsible for this bond that we talked about with our thiols that we kind of covered when we talked about thiols. Again, that disulfide bond bridge that occurs. All right, so let's talk a little bit about really something. Let's talk about some tests that can be used to identify the presence of, say, aldehydes versus ketones. So remember, as we just saw there, and as we talked about previously, we can make a aldehyde through the, again, oxidation here of a primary alcohol. And that, again, is our loss there of our H2, which will make our aldehyde occur here. Double bonding up our oxygen there. And once again, here we went from ethanol, OL, to now Al, right, which is our aldehyde. This guy, as we talked about, can then be oxidized one more time. And again, we're going to insert the oxygen in here, as we just saw on that one slide, and we talked a number of times, to make our carboxylic acid. Which, by the way, in case you're curious, carboxylic acid has the functional group of carbon, oxygen, OH. It is sometimes written as COOH in formula. So if you see that, that is sort of how it's written. And in case you're curious, it ends in OIC acid. So ethanol becomes ethanoic acid, is what that guy would be called there. So you have ethanol, gets oxidized to ethanal, which is an aldehyde, gets oxidized to our ethanoic acid, which is a carboxylic acid. We also know that, again, if we take our, as we saw, secondary alcohol here and oxidize it, we will lose our hydrogens and we will make our ketone there. Put in our double bond there. And as we just saw, this is what is known as 2-propanol. Gives us propanone. And once again, no more oxidation occurring there. So nothing happening after that guy. So we can look at these oxidation reactions and we could run a couple of tests to see whether or not we can form a carboxylic acid. Out of the two here, the aldehyde or the ketone, which is the only one that will form the carboxylic acid? It is the aldehyde is the only one that will form the carboxylic acid, right? The ketone will not be oxidized further to a carboxylic acid. So if you end up with a carboxylic acid, it's a safe bet that probably what you started with was a ketone. And I'm sorry, it was what you started with was an aldehyde and not a ketone. So if you end up with carboxylic acid, safe bet that you had an aldehyde and not a ketone. And one test that you could run to sort of determine whether or not that is the case is what is known as the Tollens test. And the Tollens test is where they use silver. And it's really an oxidation reduction reaction that occurs. So we take our aldehyde, we react it with some silver. And in this particular case, what's going to happen is it will go through the oxidation reaction and it will make our carboxylic acid, as we talked about, and the silver will actually get reduced. So this guy gets oxidized and the silver gets reduced to solid silver. Hence, what is why it's sometimes referred to as a mirror test, because it looks like a mirror silver in there. So you make like a mirror sort of film on it. So this would be a positive test for a carboxylic acid, and it would also be a positive test that you started with a aldehyde. If you ran this test on a ketone, not much happening there. Pretty much your silver is going to stay the same. It will not make this sort of mirror or solid sort of silver that's going to occur. So a Tollens test is one test that you could use to determine that an aldehyde was there and you made a ketone. And obviously, if this was a negative test for a Tollens test, it would mean that you did not have an aldehyde and perhaps you had a ketone that would not get oxidized. So again, this is a way you could kind of test what you started with. The test like you're going to do, I think this week in lab, is actually the Benedict's test. And the Benedict's test is also an oxidation reduction reaction that's going to occur. Also going to occur with an aldehyde. And it's actually a special type of aldehyde that will be oxidized in this case. But it basically works kind of the same way. The aldehyde here is going to be oxidized, and our copper is going to be reduced. And when it does, our aldehyde will then become a carboxylic acid, where we insert our oxygen right there. And our copper will go from copper 2 to copper 1. So here's the deal on this. It's actually a test for aldehydes that have really an OH group next to the carbon oxygen double bond. So it actually needs an OH group there for this test to work. Good news is the ones you're going to do in the lab will probably have the OH group there, so it hopefully should work. How do you recognize it? Well, copper 2 is blue, and copper 1 is like a reddish, orangey, gross looking color. Yes. So if you see that kind of orangey red type color develop, that would be a positive test. So if you hit that kind of orange red color, it's a positive test. So what does that mean? It means in this case the same thing, that what you started with was an aldehyde and not a ketone, because a ketone here will still not oxidize or do anything here. So a ketone will show a negative test. So if you do this test in lab and you get a negative test for the Benedict's test, that means that you're probably starting with a ketone. And if you get a positive test, then you started with the aldehyde. And if you did start with the aldehyde and needed to draw the carboxylic acid or the product, it will look exactly like the aldehyde, and you should draw it exactly the way it looks. The only thing you need to do is put the O right there, yeah, and that will get you to your carboxylic acid. So if you are asked perhaps to draw the product of that reaction, it should look exactly like the aldehyde. Just insert the O there at the end, and that will then turn it into the carboxylic acid. Nothing else will change. It'll look exactly the same. As you can see here, there's a CH3, CH3, there's a CH, there's a CH, there's an OH, there's an OH, there's a carbon-oxygen double bond, there's an H. The only difference is there's an O, yeah, and that's always where the O ends up. So if you need to draw the product of your carboxylic acid, that's basically how you do it. You just copy your aldehyde, drop the O in there, and you'll be in good shape. Here's the coloring I was saying about. So the Benedict's test here, a negative will probably still look blue because the copper didn't get reduced. If the copper does get reduced, that looks very red. In my experience, it's more like an orangey kind of color that will probably turn, will be a positive test. So you could use the Benedict's test, which is what you're going to use in lab. You could also use the tolerance test that we talked about to distinguish between whether or not you're starting with a aldehyde or ketone, because only the aldehyde should go through the oxidation. And then if you see a positive test on either of those, you know you started with the aldehyde. And like I said before, if you see a negative test, probably a safe bet in that case, you probably started with the ketone. Any questions on those there? Yeah. Now, I talked about it earlier that you can do a reduction of an aldehyde or ketone, and you will end up with your alcohols back. Let me just find a page where I could maybe draw here. So if we took our aldehyde, for example, here, and we wanted to put it through a reduction reaction, we would add some H2. So what happens in this case is it's very similar to if I had this. So if I had this guy and I wanted to add H2 to it, what do? I do what with that double bond? I make it a single bond, right? And everything stays the same. So it will look like this. The reason I have to make it a single bond is it creates room for each of those hydrogens basically to add in. So we would add a hydrogen there and a hydrogen there. When you add H2, which is the reduction, the opposite of the oxidation reaction, to an aldehyde, same thing happens. Where's the double bond here? There. And pretty much all you do is make it a single bond. So you would copy it exactly the same, making it a single bond. And now, just like you did below, you're going to put one hydrogen, in this case, on the oxygen and one on the carbon, just like you did below with that double bond. So you would lay up a hydrogen there and a hydrogen there. So I just went from an aldehyde to a alcohol. By the way, that is a primary alcohol, right? Which is the reverse of the oxidation reaction. So if I had a ketone, for example, and I wanted to reduce it by adding hydrogen or H2, go through a reduction. In this case, I should look only at the double bond and make it a single bond, right? So we'll do that. And now I have a spot for my hydrogens to come in, and just like how we add hydrogen to a carbon-carbon double bond, one hydrogen goes to one end of where the double bond was, the other one goes to the opposite end of the double bond, and now I have my secondary alcohol. So these are the reduction reactions, and pretty much what happens is the opposite of the oxidation reactions, right? The oxidation reaction is taking the primary alcohol and oxidizing it to an aldehyde. The reduction reaction is putting that H2 back on, breaking the double bond, and you'll get back your alcohol. And same thing with the ketone. When you oxidize a secondary alcohol, you get a ketone. When you throw the hydrogen back on, you break the double bond and you get back your alcohol. So the reverses of the oxidation. So going in this direction is reduction. Going backwards is our oxidation reaction that we talked about earlier. So that is basically what happens, in the reverse of those things when we put the hydrogen back on. It's pretty much identical to what happens with the carbon-carbon double bond, except it's a carbon-oxygen double bond, but works the same way. You got to get rid of the double bond to make room for hydrogens